This is a video for AQA Further Pure, second order differential equations 2, non-homogeneous equations, 2.4, particular integrals, trigonometric functions. This is just a quick recap. If you've looked at the other videos in this sequence, then you'll have seen this slide before. So here's our non-homogeneous differential equation. We start out by solving the homogeneous version of the equation, equals 0, to get the complementary function, and then we find the particular integral by looking at the function on the right hand side and using that as a pattern for our trial function. And then the general solution is the complementary function plus the particular integral. So here is our example. The left-hand side of this differential equation we've seen before, and we know what its complementary function is. What we're interested in is what happens on the right-hand side, so what the particular integral is going to be. We're going to try y is equal to, well, I've got sine 2x's in here, so I'm going to need some sine 2x's. But I do know that when I start differentiating y is equal to sine 2x, I'm going to get some cos 2x as well. So I'm going to put both bits in. I'm going to put in an a cos 2x plus b sine 2x. So if I differentiate that, the first derivative is going to be, differentiate cos, I get minus sine, so I'm going to get minus 2a sine 2x, and then differentiate sine, I just get cos, so I'm going to get plus 2b cos 2x. So second derivative is going to be d2y by dx squared, which is minus 4a cos 2x minus 4b sine 2x. So plugging those bits in, from the second derivative I'm going to get a minus 4a cos 2x and a minus 4b sine 2x. From the dy by dx I'm going to get a minus 2a sine 2x plus 2b cos 2x, and then I'm going to get minus 2 lots of y, which is going to be a cos 2x plus b sine 2x. And all of that has got to be equal to 3 sine 2x. So if I look at coefficients for cos x, first of all, for cos x I'm going to get a minus 4a from here. I'm going to get a minus 2b from the second bracket, and then I'm going to get a minus 2a from the final bracket, minus 2a. And that's got to be equal to 0. So in other words, I've got minus 6a minus 2b is equal to 0. If I look at sine x, from the first bracket I'm going to get a minus 4b. The second bracket I'm going to get a plus 2a. And from the final bracket I'm going to get a minus 2b. And that's equal to 3. So I'm going to get 2a minus 6b is equal to 3. Triple the top one, and to take them away, I'm going to end up with 20a is equal to 3. So a is equal to 3 over 20. And if a is 3 over 20, plugging that into here, I'm going to get that b is equal to minus 9 over 20. So my particular integral then is y is equal to 3/20 of cos 2x minus 9/20 of sine 2x. And then that's all of that written up neatly so that you can follow it. Again, it's quite compact, so just make sure that you follow it through. This is where we look at our trial for the particular integral. Because I've got a sine 2x thing, I'm going to have both sines and coses of 2x in my trial. I differentiate twice so that I can plug everything back into the original differential equation. And when I plug everything back in, I get this massive equation here. But by teasing out the coefficients for cos 2x, I end up with that. And for sine 2x, I end up with that. And if I put those together as a pair of simultaneous equations, I can get values for a and b, which gives me my particular integral. So if we've got this differential equation with this right-hand side, we know the complementary function is this, and we've seen that 2 or 3 times by now. And the particular integral we've just seen works out to be this. And we know the solution is the complementary function plus the particular integral. So I get complementary function plus the particular integral. So here's a couple of plots for this general solution. The left-hand one has fairly small values for a and b, 0.01 and 0.02. The right-hand one has somewhat larger values, a is 1 and b is 1. In both cases, however, the driving factor for both solution curves for large values of x is the functions that involve e. So the blue line here is the e to the 2x bit of the general solution, and you can see that as x gets large, the curve tends to that. And similarly, the green dotted line is the e to the minus x part of the function, and as x gets large and negative, it tends to that fairly quickly. The wiggling around in the middle is related to the cos and sine curves, which give you obviously an overall sine type function, and again we've seen that in a previous video. If you look at the right hand one, you'll see that because a and b are so much larger, the effect of the wiggle in the middle is somewhat ironed out, and that means that these two parts here don't really have as much effect in the middle. They're overshadowed by the size of e to the 2x and e to the minus x. So let's have a look at an interactive plot for this general solution. And if I take a down to 0, you'll notice straight away that the solution curve looks just like a sine curve, periodic function on the right hand side here, and that's because the rest of this is disappearing. There are no e to the 2x's. E to the minus x, as x gets large and positive, it's vanishingly small. So we've just got this combination of cos 2x and sine 2x, which we know can be represented by a single sine function. If we do a similar thing for b, the same thing happens, but it happens on the left hand side this time, and you'll see we haven't got any e to the minus x's, and e to the 2x is vanishingly small back here, so everything is being driven by the cos and sine functions. What happens if either of them is negative? Well, all that happens is you get this reflection in the x-axis on the left hand side here, and if we switch it over so that we've got a is negative, we get the reflection for the e to the 2x type function. And if we have them both negative, then you'll see we've got reflections for both of them. So everything is basically turned upside down. Okay, so we're starting to collect together some of the trial functions we can use for different types of right-hand function. And we've seen linear and we've seen polynomial, and now we've seen trig functions. And whether it involves just cos px or cos px and sin px, we would always use both of them. So we'd always include both a cos px and b sin px in our trial function for the particular integral. The next video in this sequence is 2.5 Particular Integrals Exponential Functions.